Hello everyone, it is I, your internet friend, Robert Gadarian. And today we are moving on to recursion. And there is going to be, this video will basically say what it is and the simplest way to solve problems. And then we'll have a large demo that is slightly out of scope for this class. And then we'll have some smaller demos just to show you some stuff, because this is best served with a demonstration. But first of all, what the heck is recursion? Well, it is a problem that keeps on happening, and it is the same problem. And there might be a couple dad jokes thrown in. Okay, so consider a recursive problem. 5 factorial. 5 factorial is 5 times 4 factorial. 5 times 4 times 3 times 2 times 1. So as you saw in the slides, there we go, that 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is equal to 5 times 4 factorial. So when I say there's two problems of the same type, I mean this. These are both the same problem, but a different input. So they're of the same type. They're both factorials. So that means that we actually probably could solve this by saying this is 4 times 3 factorial. Yeah, we could. And then we could solve this by saying this is 3 times 2 factorial. Cool. And then we can say this is 2 times 1 factorial. And then 1 factorial is just well known to be 1. And then we could say, okay, well, I have 1. And then that is going to be 2 times 1 is equal to 2. So we're going to return up 2. And that's going to be 2 times 3 is equal to 6. 6 times 4 is 24. And I've made a huge mistake and I have to multiply 5 times 24. And that is definitely equal to a number. So you don't come here for the math. I have a computer to solve math for me. That's as far as I can go. So we have a repeated problem. We can say there's a subproblem of the same type of problem. And it's really important that we have a subproblem. If it's not a subproblem, you cannot solve it with recursion. I can't say that often enough to you. So how would we code this up? So we'd have a function called factorial, and that function would call factorial, which is a function calling itself. So blank page, def fact. We're going to pass in n, which is the number we're factorialing. And then that is simply going to be we'll return factorial of n minus 1 times whatever the heck we have here. I'll write it the same way that I wrote it. I said 5 times 4 factorial, so I'll say n times n minus 1 factorial. So if we switch over to our piece of paper, we have that here. We have n is equal to 5 times 4 n minus 1 factorial, 4 factorial. We have n minus n minus 1 factorial, n minus 1 factorial, all the way down. Okay, good. So this is our code. I'm going to call it print fact 5. And well, I'm going to say 4 because I can actually do that math in my head. And as we know, because I've harped on it quite a lot this term, make sure you can actually predict what output should be. Maximum recursion depth exceeded. What went wrong? So this is approximately the function I wrote. I put in 4 in my real example. And let's look through this line by line. It's like I predicted that I'd do this wrong. So my function calls fact on n minus 1. So from here, there we go. My function comes in, is going to take n times fact minus 1. So I was going to call this function on, well, this is 4, so we're going to have 4 times factorial of 3. So now n is 3, 3 times factorial n minus 1, 2. 2 times n minus 1 factorial, that's 2 times 1 is 1. Factorial 1 is 1 times 1 minus 1 factorial, or 1 minus 1, so it's going to be 0. 0. 0 times factorial of n minus 1. So minus 1. That's not what I did in my work. Minus 2. Minus 3. Minus 4. Minus 5. Minus 6. We didn't stop. And that is the most common problem you'll see if you are doing any kind of recursion. Things happen. And we never stopped. So this is like infinite looping. While true is an infinite loop, we'll never stop. This is called infinite recursion and does stop when our computer says, I can't do it anymore. Python, I believe I tested this last year, does 1024 recursions before it says, nah, I can't do that. So what we need, let's go in with some expectations of what we need to do. We need to call our problem with a subproblem. If we don't have a subproblem, if factorial 5 is equal to factorial 5, it'd be an infinite loop again. So we'd have 5, 5, 5, 5, 5, 5, 5, all the way down. And that doesn't work. We can't do that. That is a recursive case. We need a subproblem. 5, 4, 3, 2, 1, stop. Good. And we need a well-known time to stop. You saw that in my little doodle here. Where did we stop here? We stopped at 1. 1 factorial is equal to 1. So we're going to say fact. 1 factorial is equal to 1. So this is now our base case. I will always call it a BC because I'm lazy. And a recursive case is factorial of n is equal to n times factorial n minus 1. Okay, do I have a subproblem? Yeah, I do. I have a subproblem right here. And I have a place I can stop. So now with those two facts, I can go all the way through and have a definitive place to stop. Very important. Oh, there we go. Sorry. I forgot which one my key commands was. So what am I missing here? I have a recursive case, and it is a subproblem. But I don't have a base case. So I'm going to say if n is equal to 1, I'm going to stop. So I'm going to say out is equal to 0, just to set it to something, because most programming languages require that. Python actually doesn't, but I'm sorry. I'm a generalist. Out is equal to 1. Otherwise, we're going to say this. Chop it. Out is equal to what our recursive case. So now I can even put in comments. This is our base case. This is our recursive case. Oops, there we go. This is our recursive case. And now I have everything. I will say if n gets down to 1, we can return 1. Otherwise, we're going to multiply n, and whatever the heck the rest is, and we can now assume that will stop. And we can trust that this works. And this is the crazy thing about recursion. Recursive case, base case, and pray. At this point, we're at the pray part, where we have to have faith that we built the function that we're calling right now correctly, because in order for the function that we're building right now to work, it has to work. And that is something that people get freaked out about recursion. You have to have faith in yourself. Does this factorial function that I'm currently writing work? Because I'm calling it and it needs to work. Well, yeah, it does. Because I've fulfilled all the requirements. I have a subproblem. That is my recursive case. And I have a base case. That is getting called. Boom. 24. And that is what I calculated in my doodles. Indeed it is. I just pointed at it, but I actually have to underline it. 24. Huzzah. We did it. Very cool. So let's try another one. Palindromes are the words that are read the same way forward and back. Dr. Awkward, wow. There's lots. Just Google palindromes. There's plenty. So let's do that. I'm going to switch over to my codes. This is your classic recursive method. Def pal is usually what you call it. And then you have some data or some string. And I can't name it string. I need to name it word. And I want to prove if my word is a palindrome. I will return true if it is a palindrome and false otherwise. So we need to doodle this out. And without doodles, you're done. So we have some word. And we need to see if it's a palindrome. So I'm going to start with wow. I know, lame, but fine. So what I'm going to do is find a recursive subcase, where we're going to check if the first and the last are the same. If yes, I want to check if the middle part is still a palindrome. I'm not going to spell palindrome. And then we'll keep on doing that until, and this is my base case, we have one letter, which is by definition a palindrome, or 0 letters, which by definition is a palindrome, which feels a little bit like a stretch, but it's true. If you have no text, it's a palindrome. And these are my now 2 base cases. Oh, wow. Does that make it any more complex? Not really. Let's do a slightly longer one. So Dr. Awkward. Very appropriate for computer science, and especially me. We're going to grab these 2, and we're going to say, are these a match? Yes. Then we grab out the middle, and we'll say, this is now my recursive case. I'm not going to rewrite it. I will rewrite it. So we'll have R, were. Now we're going to check the first and last. And is R equal to R? Indeed it is. Move down. Then we're going to have wa. Check the first and last. Check the first and last. I think you get the picture. And Python's very kind about this too. How do we get the middle slice? Okay, we're going to do it. I'm done. Okay, so boop. We're returning true if it is a match. So base case first. Is the length out is equal to something? Doesn't really matter. If the length of our word is less than or equal to 1, we can't actually get negative length, so this is actually safe. Then we're good. A little bit redundant. I can make this shorter, but I'm not playing code golf right now. If you want to check out code golf, it's hilarious. Else, recursive case. Now we have to look at the rest. Well, first we have to match and then look at the rest. So first, is this still a palindrome? Palindrome. Probably spelled right. Palindrome? Palindrome. Check first and last letters. If our first letter, word, spot 0 is equal to our last letter, word, at spot -1, because Python's awesome, then check the rest. If not, we failed. This is a base case too. That we failed. All right, check the rest. What do we do? That is, we're going to say we've proven that our 2 letters that we have currently are indeed these. So we're going to get this middle slice, and we're going to see if that is a palindrome. And my results of everything else is the rest of me a palindrome? So I'm asking a question, and it will return true or false. And all my job is to, here, let's go all the way down. W, K, W, K. This is going to return true. 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 And then out goes true. So we bubble up this answer by saying, well, I know my part is a palindrome, so let's check the rest. Pal, and I'm going to slice this word starting at letter 1 and going up to and not including the last letter. And I will save this, apparently. Pal. And I need to actually call this at some point. Print. I'm actually going to make a nice little function for myself. This is called a bootstrap. Def is pal. And I'm going to have a word. And then I'm going to say print. Then a placeholder. Is blah a palindrome? And Rome, question mark. And then placeholder. And then I'm going to do a dot format. I haven't done a dot format string in a while, have we? Word. And then pal of word. So this will give me a nice little printout. I'm going to say is pal on wow. Oh, I'm going to make it all lowercase with no spaces. That is, we can strip it out pretty easily. If you want a challenge, it's actually kind of cool. Taco Cat and Dr. Awkward. If this thing ever ends, come by my office. I have a Taco Cat painting from my niece. Why not? Is pal Rob. Hot tip. That one's done. I have a warning. Local variable out is never returned. Let's return out. That'd be a great idea. So that's what I was complaining about. Okay, that is tiny for you. Beep, 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 beep. And is wow a palindrome? Yes. Is Taco Cat a palindrome? Yes. Is Dr. Awkward a palindrome? Yes. Is Rob a palindrome? No. And we could actually do some more debugging. There is the weird edge case of just one letter. And this is something I could catch by Bootstrap. Is pal an empty string? Is that a palindrome? In our definition, yes. In our isPal function, we could check to see if they gave us a zero-length string and return false as a weird edge case. And that works. And it's all about this stack. And that's what this is called. It is actually using a stack data structure. It's kind of cool. So we're going to be passing down all these little pieces of data, and then it's going to remember each state. And this is just like calling a function. We're just asking questions. And if you look at a single line of code in here, all we're doing is calling a function, and then we're going to return the value from that function. That's all we're doing here. And from our view of writing this, we've just checked, we are a palindrome. Is this substring a palindrome? And then return that value. That's all we're doing. So the funny thing about recursion is that you always have to dumb yourself down and just think about recursive case, base case, pray. That's it. This one actually has a couple base cases, but it's not too bad. Is this dumb? This would never happen. Nah. So if you do a lookup in a phone book, how do you do it? I mean, do you have phone books? Let's say that you have a monster manual. Fun fact, also in alphabetical order. What are you going to do if you're looking up owlbear? Well, you're going to jump to the middle, and you're going to say, oh, I'm looking at M. Is O greater than or less than M? And you'd be like, L, M, N, O. Okay, it's afterwards. I've just eliminated half this book. And then there's a recursive case where I'm going to eliminate another half of this book. And I'm going to flip over to R. Okay, so I know that it's... I'm here. I'm looking at a Rakshasa right now. And is O greater than or less than R? Well, O is less than R. So that means that O is in here somewhere. So we're going to jump into the middle of that. Somewhere. Okay, where am I going? So now I'm looking at micronids. Okay, I've already done M, so I know that it's going to be in this bit. Jump into the middle of that. Woman oozes. Owl is after ooze. Oh, and then in 4 lookups, I found my owlbear. And if you don't know what an owlbear it is, go hoo hoo grr. And that is a recursive problem. I just said, I have this data. I'm going to look in the middle, and then I'm going to eliminate half my set, and then I'm going to look in that data. And then I'm going to look in the middle and say, is it on the left or right side? I'm going to eliminate half that data. I'm going to look in the middle. And that is called a Oh, I'm blanking. Oh my gosh. Binary search, where it is recursive. You're looking down, and finding a single base case. And my base case was I'm looking for an owlbear or it's not there. And I can do that because it was alphabetically ordered. I can just eliminate everything. So when you're doing a lookup in a phone book, you're using recursion. File systems. We're actually going to be doing an example of this next lecture, and it is something that I find everyone has to do at least once in their life, so I'm going to show you how to do it. So recursion, we need a subproblem of the same type and a stopping point, and you know what, usually this turns into really short code. I'm sorry, this is the best meme of the whole class. I hope you're having a good day, and I'll talk to you next time.